So as we've talked about, if primary alcohols get further oxidized from an aldehyde, they'll become a carboxylic acid. And if we have a look here at a carboxylic acid, it's at the end of a chain, so always at the end of a molecule. And we can identify it by the fact that the carbon is attached to a double bond O, but also to a hydroxyl group. So the difference between this and an alcohol is that that carbon that's attached to that hydroxyl group must also be attached to a double bond O group or a carbonyl group. We name them by enoic acid, so in this case where there's two carbons, so one here and one here, this is ethanoic acid. So in the case that there was 3, this would be propanoic acid. A way that we can test for them, because it's an acid, we could react it with a carbonate and see if there was any fizzing, so we would notice effervescence. A bit of a reminder here, you're not going to be able to see hydrogen gas or carbon dioxide gas. So if you're reacting the acid with a metal such as magnesium, you're not actually going to see the H2 gas, but you are going to see evidence of bubbles like you can see in this picture here. So if you ask for an observation, it would be bubbles that you saw. Alright, so with our carboxylic acids, because we now have two polar regions, the hydroxyl group is capable of forming hydrogen bonds and the carbonyl group forms dipole-dipole interactions. We're going to have a much higher melting point or boiling point for our carboxylic acids than we are for our aldehydes or ketones due to the increased number of polar regions. We will also have a higher boiling point than our equivalent alcohols because of the extra polar region. Alright, and additionally, because carboxylic acids are an acid, it means that they donate a proton. So the proton they donate is this hydrogen here as part of the hydroxyl group. So let's take a look at the carboxylic acid in more detail. So carboxylic acids, so let's take a look at ethanoic acid. If we added carboxylic acid to acidic conditions, we're going to have nothing occur because it's an acid reacting with an acid. If we added a carboxylic acid to basic conditions, so sodium hydroxide for example, we would end up with a carboxylate ion because we've got an acid plus a base here. So an acid plus a base we know forms salt and water. We end up with an organic salt. So we get our carboxylate ion, so this is the ethanoate ion. We will then get our sodium in this case because that's the salt that it's going to form. We'll get sodium ethanoate here, and we then get our water forming as well. Now because this is no longer a carboxylic acid and it's an ion, we get much stronger secondary interactions with water because we get ion dipole interactions which will make it soluble no matter what size the salt is. So if we have a really long chained carboxylic acid, we can make it soluble just by putting it in basic conditions. Similarly, if we wanted a carboxylate ion or carboxylic acid back out, we can take this carboxylate ion and put that back into acidic conditions, so add our acid back and get that carboxylate ion turned back into a carboxylic acid. So this is really handy if we wanted to precipitate something out, we can use these properties, but it's also really handy if we wanted to make something soluble, we can put it into some basic conditions. Alright, so let's take a look at an application of where we want molecules to be soluble. So we've got two examples here of over-the-counter drugs, so a salicylic acid, which you know more commonly as aspirin, and ibuprofen, which is a main ingredient in something like Nurofen. And we can see in both of these we have the carboxylic acid group, so we've got the carboxylic acid group here and here. And that's really handy because that means that we can make these water soluble. So if we can turn both of these into the iron form, we can have these quite non-polar, so we've got quite a lot of non-polar groups in both of these molecules, and what we can do with them by turning them into the iron form is make them soluble, which makes it a lot easier for us to digest, and it means it'll take up quicker into our system. So the way that we do that, so it's important to note with these that if we didn't do this, these would not be soluble. So as they are, these are not water soluble. So the only way to make them water soluble is to turn them into their ions. And what we know about both of these is that when we buy them over the counter, they're in a tablet form, so it's all powder. So in the mixture of aspirin or ibuprofen, we have a sodium hydrogen carbonate mixed in with these. So we know that when we put aspirin in water, we get that fizzing occur, and that's because we're getting the acid-base reaction. So we're getting the acetylsalicylic acid or aspirin mixing with the sodium hydrogen carbonate. And so as they come into contact with the water, it actually makes the reaction occur because it creates an aqueous environment for acid and the base to come into contact with each other. As they come into the contact with each other, this hydrogen from the acid gets donated, because we'll remember that acids are hydrogen donators or proton donors. And as that happens, we get a negative charge on the oxygen. This sodium then binds with that oxygen, so we get sodium plus acetylsalicylic acid becomes a minus overall charge, so making it an ion. And because it's in water then, they're soluble. So we've got two ions in water, which means that they can then form ion dipole interactions. And those ion dipole interactions make it soluble.